on our proof of Kim's theorem for a lower bound for R3K. And what have we done so far? We've defined a random process, which is like the triangle-free process, but turns out will be considerably easier for us to analyze. And I just finished by saying, OK, last time, by stating a bunch of quasi-randomness conditions that I want these two graphs. So at every stage, what do we have? We have these IID samples. I have these graphs G1 up to GI, for which these are the pieces of my random graph that I've built up so far. This is my triangle-free graph that I'm building. And I'm also recording this set of open edges that are legal for me to put into my graph. And there was some trickiness in how I constructed this set. Good. OK, so the thing that we're really most interested in is how this OI and this GI prime look. And we'd like to say that these two graphs look somewhat like a random graph, two IID samples on the same vertex set. OK, and where we finished off last time is I just wrote down a bunch of properties that I want these graphs to have at every stage. So this is this event AI, which will show holds with high probability at each step. And the event is defined by these things. OK, so what do these mean? I want my good sample. So when I go from step I minus 1 to I guess I've written it here. I want my density to be roughly close to what the expected density is. So this is the density of my open edges. OK, so nothing crazy happening there. OK, and we'll talk about this more in a second, is I want the size of every neighborhood of open edges to be roughly what I would expect. So this is the density I expect. And I'm allowing a bit of error on the upper tail. This epsilon I, it's not going to matter a lot for us, but it's just some error parameter. And I can choose something like I times gamma cubed or something. Remember, gamma was like 1 over some polylog. Yes?
OI are open in GI or GI prime?
So OI are the open edges at stage GI. Every edge in OI does not form a triangle GI primed, but it's also a subset of it. So not every such edge. We sort of refined it further. Thanks for that question. OK, so this is I have the right number of edges. Also, the codegrees are nice of this graph. So if I have x and y, and I look at the common neighborhood of open edges, that's what we expect, right? I expect a theta I squared factor. OK, I get it up just this error. OK, also I want my GI prime to have this nice degree and codegree condition. But actually, this is quite easy to prove, right? Because this GI prime was just some IID samples. So these conditions, I didn't write max degree condition and max degree condition, all actually follow quite easily from these. OK, so I won't spend too much time talking about that. And there's one condition I want to bring your attention to, which is where the two graphs interact, which will be quite important for us. So this is, I look at the degree in my graph GI at most 1 prime, and look at the intersection. Where should I put my y? Y. So this is vertices with edge there, open edge there. And of course, this will be important for, as we'll see in a second, controlling the number of triangles. Number of open edges. OK. And what I'd like to do, and really the main task in proving that the process runs to this final time, which I forgot to tell you, I forgot to remind you what it is. So some small delta divided by gamma over root log n. So if I want to show that my process runs all the way to this time, the key task here is showing that this holds at each step. OK, but what I'd like to do first is just assume that this holds with high probability, or just assume that these events hold, and show that my process will actually run that long. OK, and then I'll come back and talk about how to prove this. OK. So let's write down some lemmas. OK, first, I would like to maybe I'll just call them observation, because these are all going to be very short. I'd like to make rigorous something that I said before, but let's just completely write it down. So here I'm interested in my graph at step I, and I go to step I plus 1. So, let for some I, let E. So I've imagined I've fixed this graph, and I've fixed a set of open edges, and I've fixed some open edge in this collection of open edges. Okay. Then the probability that E remains open into the next round, so now this is my randomness at step I plus 1, this probability is constant over all edges. So it doesn't matter what open edge I choose. So in particular, it's equal to the minimum of E in OI times this probability. OK, so I'm actually going to write something that will be useful for us in a second. Remember, I had the condition for surviving into OI plus 1 was the probability that you survived into OI plus 1 prime, and you also survived this independent coin flip, which possibly dropped your probability. So we actually chose the probability precisely so that this happens. OK. And notice here now that the right-hand side doesn't depend on which E I choose. Is it clear? OK. And the proof, I'll say then, and since this is now just a fixed quantity, I'll define this. This Si plus 1 is the survival probability for an edge. Right? So it's the same everywhere else. So it makes sense to define this Si plus 1. OK, so the proof is really by this refinement step in the process. So let's just write it down. So the right-hand side OK. So the condition for surviving into OI plus 1 is the probability that you survived in this percolation step. This is in this Q, I plus 1. And independently, you had to survive into this round. But now what is this probability? This probability is precisely this divided by this. And so we get this. So I'm out of space, so I won't write it out. But it was actually just defined, so that holds. I don't want the prime where? Here? This is correct. So you want the primed here. Right, so this is the smallest after the initial round. And then like the percolation round, make sure that it brings all the other probabilities down to this minimum. Right, they're equal in that case, yeah. Thank you. But this is the formula that I'll want in a second. Okay. Right. All right. Okay. So now I want another observation here. Well, actually, maybe I'll just write it. So I really care a lot about this theta I. And in particular, it'd be extremely bad for me if my density of open edges is dropping really fast. Right? Because then my process is going to stop prematurely or faster than I'd like. So that's what I'm on a quest to understand now. The first thing to notice is the following. So let me just write down, actually, this is just, again, holds by definition. Whoops. So here I'm imagining I've fixed my graph at stage I, and now I've done my I+1 sprinkling, and I'm interested in the probability, so the expected density of open edges after this I plus first step. Okay, by definition, this is equal to what? The probability. So how many what was the density of edges before sprinkling? Before I did anything, it was this. What was the probability that an edge survived into the next round? It was this by definition. So in expectation, this is the density, right? So if you want to write that out formally, you're just summing over every edge and asking what's the probability you're in, summing it up. And now I wrote density, so I just divide by and choose 2. OK, that's just true by math. OK. Now here's where things get a bit more interesting. OK, so assume that AI holds. OK, so again, we're standing at step I, and this graph, I promise you, satisfies these nice well-behavedness conditions. I'd like to say something about Si plus 1, the number of edges that get lost at that stage, or survive at that stage. Then, Si plus 1 is at least, there's an error term here, which I'm not going to grind on too much about, but it's going to be something like that for sure. Minus 2I plus 1 gamma squared. OK? So this is a slightly mysterious quantity at the second, but we'll get used to it. Let's prove it. OK, so this is my thing of interest. I have a formula of it for over here. Let's focus on the E that attains this minimum. OK? So I'll just write it, whatever, the minimum. Minimum, so might as well write the whole thing. OK, min E. Probability E is in OI plus 1 primed. OK, so what is this? Now we're actually hitting the rubber hits the road. So I need a picture. Here's an edge that was open at stage I plus 1. And what am I asking? What's the probability that it stays open in this sense, the prime sense, into the next round? So this is what it would mean like to be closed if there was something like this. So where would that come from? One way for that to happen is you look at the closed neighbors here. So this is Gi prime at most I. Look at the neighborhood of X. I'll call it X and Y. Intersection with the open neighborhood of Y. So this is I prime intersection open neighborhood I, Y. Okay? And if it's going to remain open, you better miss all of these edges. Otherwise, you would have formed a hat on this guy. OK. That's one way for it to close. Another way is switch the roles of X and Y, so closed, open. A third way for that to happen, I don't have a lot of space. I don't need this anymore. Third way for that to happen is getting two edges like this and this in the open neighborhood. So if this is the neighborhood I, Y, right? OK, and that's the only ways to form this. So now let's just write that down as a probability. OK, so what's the probability this happens? This is like 1 minus pi plus 1, because it's my I plus first sprinkle, times the size of this. OK, I want a lower bound for this probability. So I want an upper bound for the size of this. that's exactly what I got here. Okay? I'm just going to drop the error terms here just because they're a little bit confusing. So I have this term, and I have it times 2 because I have it this and for it reversed. So that's 2 theta I gamma root n. OK. And now there's also this guy here. Now I have to have 2 edges to complete it. So it's going to be 1 minus pi plus 1 squared to the power of the maximum size of this open neighborhood. I also have control on that from here. So this is like theta I times n squared. OK, and now it's just a little bit of math, and out pops our number. OK, so let's see if I can fit it. This is at most x minus, OK, so pi plus 1 times theta I was designed specifically to be gamma over root n. Because I'm always sprinkling the same amount of edges at each stage. This is like an important thing. So 2 theta, oops, that disappeared. I gamma squared. The root n's cancel. So I get this. And then on this side, this is going to cancel with this and leave a gamma squared. Sorry, I forgot the minus sign. And that's it. Sorry, wrong way. Thank you. Yeah, sorry, I was thinking of upper bounding these quantities. Thank you. Good, and so I get this, check. Right, so we really see that these conditions feed directly into understanding O. OK, and now I can really start understanding something about how my process runs. OK, so in particular, let's take this one step further. What should I say? So the expected value at OI plus 1, sorry, observation, if these events held at every step up to I, OK, I can just sort of iterate this expectation. So now let's take the expectation over the whole process up to that point. And this is just going to telescope, right? So this is going to be Si plus 1 times whatever you had at the previous step, but expectation of that. So Si all the way down to S1. So this is basically going to be at least x. I'm kind of dropping error terms again. I'm just going to be summing this exponent, which is just going to be, so it's the sum of odd numbers, which is going to be I plus 1 minus I plus 1 squared times gamma squared. OK. OK. Now this just holds an expectation, but that's why I needed some condition like this. Because I wanted to say, when I step to the next step, that was a good sample if you were always close to the expectation. So I can actually say, I can also delete the expectation from this. So I don't want to bore you with just checking the errors here, but using property 1, we actually have on this event, theta I plus 1 is at least basically this business that we want here. OK. OK, and now this is really good news for us. Because what are we trying to do here? We're trying to understand how long the process runs. And the only way that it can stop is basically if theta I gets too small. OK? So process stops if and only if, just by definition, theta I, or let's say theta final, is gets extremely small. So it's like even, this is overkill for us, but something like this. Right? This is basically the point. There's no point in even proceeding. I won't check that. But now we just need to compare this business with this business to see when this process will stop, assuming that we can preserve this event A1 up to AI. Okay, so maybe I'm a bit too careful about preserving this. So let's just delete this. OK. So just note, if we plug t in here, so t was what? It was delta over gamma, delta just a small constant, log n. Let's plug that into here. So that will be the time that we're just going to artificially stop the process. We don't care to go any later than this. This is basically t squared, gamma squared, which is just see how things cancel out. And this is basically n to the minus delta squared. Right, so for us, delta is going to be a small constant. So we're well away from that n to the minus a half business. So we're nice and happily running until time t. OK, so if we can show the events hold with high probability, this implies process definitely runs, or with high probability, runs to time t, which we feel good about because that was our whole purpose in this discussion. Okay. Is there any questions at this point? OK, so in order to show a process runs to this point, all that's missing is to show that we can preserve these properties in each stage. And it turns out this is also quite easy to do with this modified process. Yeah.
Where did you use the fact that OI prime OI is concentrated? Theta. Yeah, the theta.
Theta.
Yeah.
Here, because we know that it holds an expectation, but I actually want it to hold with high probability here. So it's just from here to here. OK. Great question. OK, so now I'd like to show that these AI holds as the process runs. So what I'd like to really do is just, I'm going to show it by induction. Assume it holds for a graph AI, so sorry, at step I. And now I want to show with high probability in my next step, the graph also has it. And interestingly, key to this will be the following basic geometric lemma. So, or not geometric, combinatorial lemma. Wrong talk. OK, so lemma. And basically, once you have this, you just kind of slice and dice using some basic ideas, and actually, you just automatically all the properties will follow. OK, I think this lemma is actually quite nice. OK, so here again, I'm stopped at step I, and I go to step I plus 1. So assume sort of that we're at step I, and that this business holds. OK. And now say I'm just given fix some subgraph in your set of open edges. Okay, so just some set of edges sitting inside of your open edges. And assume that it has the following two properties. So the max degree, I want to be not too big, like some polynomial. In fact, I can even put a small constant there, but then I have to think of a name for it. And the second thing I want is when I look at my graph at step I, and I look at so what am I doing? Here's my h. It sits on some vertices in here. In my bigger graph, I just want to make sure my process hasn't stuck too many edges inside of this world here. So this I'm going to also assume is little o1. Okay? OK. So now I'm going to throw down my next step. I'm going to ask the question, what's the probability all of H survives into the next round? So what's the probability H lives entirely in the next round? OK, so what's your guess for this number, right? So the survival probability is this S sub I plus 1. And I have this graph, and I want all of the edges to survive into the next round. You'd expect that they're kind of independent. So you would guess this survival probability to be something like this. Okay, and this is what we prove with some error term that I've conveniently left a blank for. So it doesn't matter so much what this is at this moment. Oh my God, looks terrible. OK, it does matter more than that, though. So this is going to be 1 plus n to the little o1 times pi plus 1. OK. So what I want you to take away, forget this n to the little o1. This is a pi plus 1. Now, pi plus 1 is always going to be pretty small. It's always going to be around n to the 1/2. In fact, I could have written that as the corollary here, because pi plus 1, wow, that was a big P. OK. Pi plus 1 is gamma divided by theta I divided by root n. And this theta I never got too small, as I just told you somewhere that I deleted. So this is always equal to n to the minus 1/2 plus delta squared plus little o1. OK, so it's always like pretty within delta squared of 1/2. So this is a nice small term. Good. OK, so the proof of this, the sort of formal proof of this result, I put in the problem set using some tools that we've built up from the other problem set. But it's actually very easy to see why it's true, or not, like almost rigorously. So I'll just give a proof sketch of this result. OK. Let's look at the time. Very good. OK. OK, so here's my graph H, OK? It doesn't have to be an induced subgraph or whatever, but I like to draw a blob. So there's a bunch of edges in here that are hanging out. And these are all part of H, and I like them all to survive into the next round. OK. Now, maybe let's order the edges. Right, E1 up to E, I think M is actually free. OK, amazing. Like that. And I'm also going to define the useful quantity, which I'll call y of EI. OK. Now, each one of these edges can get closed in these two confusing different ways, right? One is that it could close a triangle. So that was already from a previous stage. That was open, and then I sprinkled that edge in. And now I closed it. Or I could close two open edges. Let's forget about that latter one, because it's a bit confusing. Let's just pretend the only way to close a triangle is to put a single edge in. It's not so hard to mix in this other thing, and that's kind of your exercise. So for each EI, let's draw a nice big EI over here. Let's write all of the edges F in the entire open graph that could potentially close E if it were to get added. So this is all F such that we have this config in the graph. So this is EI, this is F, and this is already in the graph. OK? So in other words, that edge better be avoided. In fact, we have to miss, if this event is going to happen, all of these edges that are in all of these sets, the union of YEI. OK? So what's this probability, roughly speaking? Let's just call this something, star. So star is equal to 1 minus p times the union of this yei. Okay, and there's also another term with p squareds, but I'm tactfully forgetting about that right now. This is the dominant term, and this is actually pi plus 1. Okay. Now, I also lied slightly because there's also this product of qi's that are balancing the probability. This is just the probability of surviving into I plus 1 prime. There's also the q's. qi. I'll maybe do q, sorry, e sub I is what I meant. I equals 1 up to that. And now all I want to do is just make a very simple two simple observations. Okay, let's just write this as, at most, 1 minus p. So actually, let's do it dynamically a little bit. This is not strictly necessary. You could just do algebra, that's fine. Let's look at the first edge. I explore the first edge. Right? I explore a bunch of things, and I ask, how can it survive? Okay? And then I multiply by this q, e whatever, e1. So the e1, like that. Okay, by definition, this thing is basically just si plus 1. Right? Okay, there's technically another term with the two pairs, but we're forgetting about that. So this business is just, by definition, si plus 1. Okay? Now let's explore another edge in my collection. Here's E2. Same thing. E2, x E2. And this is going to give me another si plus 1, and so on. M, x. Okay, where if I cheated, these sets might overlap. So for example, a set that I saw in some y sub, oops, I meant to write y's. I saw in some earlier y I could have encountered later, and then I'm not allowed to count it again. Okay, so it's equal to this. Si plus 1 to the e of, for every edge, which is e of h, or m. But then I double counted how much? Basically, a 1 minus p minus all possible intersection sizes. So this is yei intersection yej, something like this. So I just need to control this business. And I just want to sketch how you do this. It's actually very simple. Is how could an edge contribute to this sum? Okay? So here was some ei, and here was some ef. Sorry, ej, rather. Okay. If you're in this intersection, you're an open edge, and if I put you in and I close both of those edges, in this picture, you have to look like this. So open, closed, closed. So how many right, so if I put this in, I close both of those. Okay, how many such configurations do I have? How many such bad pairs? Well, first choose E1. There's E to the H choices of E1. But now the degree here is n to the little o1. So there's n to the little o1 by this choices of this endpoint. There's n to the little o1 choices of this endpoint, and that's it. Okay, so there's that many ways of choosing this. But there's another way for two edges to be. They could be adjacent. So I could have this picture. Here's EI. Here's EJ. OK, there has to be some edge that closes them both. It has to look like this. And now we're going to do some similar counting. How many? Sorry.
Can you explain why there's n to the 1?
Right. So, because I pointed at the wrong thing precisely. Right, because so every edge here contributes to the graph induced on this set of edges. Yeah, thank you. Yeah, so sorry, by this condition, not the one that I pointed to. Okay, and similarly here, we have two adjacent edges. How many configs are there like this? Sorry, so adding f, of course, will close this and this. Again, there's e of h ways of choosing this ei. How many ways they're choosing this edge? Now I use the other degree condition, the one that I bring this one. So there's that many open edges adjacent to this, right? This edge had to lie in H, okay? But there's n to the little o, one of those. So now I fix these two, and now I use my co-degree condition. These two vertices, these edges come from the previous graph, and I said there was at most log n squared vertices that were in the co-degree. So that's also n to the little o1. So I get this up here, and this is contributing here. So those are the two kinds of term. I sum them up, and that will give the error term. Good. Any questions about that? So that was a little bit fast and loose, but it's really not much more than that. Okay, so this is all very simple, but this simple lemma actually does quite a lot of work for us. And what I'd like to do is derive 2 of those 5 properties just using this simple lemma. Okay? So the first thing I want to do is show that the concentration of the open edges into the next step. So assume AI holds. Then theta I plus 1 varies from its expectation by some small amount here. There's also I plus 1. And the probability this happens is at least 1 minus n to the c or something like that. We'll actually see what number comes out here. Sorry, minus c. Okay, and we're very sophisticated people here, so we like to use very sophisticated tools. How do you prove concentration? Right? I just want to use second moment argument. Right? So, okay, let's use edges instead of density. Maybe it's slightly nicer, right? So you agree if I could show that the number of edges, so this is going to be the number of open edges at state I plus 1. If you can show that this is concentrated, that's the same as this, right? It's just a factor of n choose 2. Okay, maybe I could even, whatever, okay. Okay, so the expectations are all going to work out by this. So the expected number of open edges is just going to be the number of open edges in the previous graph and choose 2 times the probability you survived. Remember, we're thinking of this as a fixed number here, right? So this is the randomness is here, because I've fixed my graph at step I. Okay. Oh, and by the way, this number here is precisely this expectation by something I wrote before. Okay, so all the expectations are matching. How do I do the variance calculation? Okay, if I do the variance calculation, I just need to calculate the second moment. So expected value x squared is now, okay, so let's write this as a sum. I don't want to actually write it, but this is a sum of indicators over all edges, right? That's a big sum, and then I square the big sum, and all the guys hit each other, and I get the following sum. So this is overall EF that were open in the graph you gave me, times the probability E and F remain open into the next step. Okay? But now I actually now know how to compute this probability, because I know something about the correlations. E and F, this is a graph on two edges. So it's a very humble application of this previous lemma. So H is just equal to EF. And so this lemma says that I can factorize this business. Oh, I won't be able to write it there. Too bad. Factorize this probability and call it a day. So this is at most 1 plus some error term, which I don't care too much about. I'll just put something like this. OK, the number of edges is what? 2. So I'm not even going to put the 2 here. Times the sum of E in OI times the probability of F in OI. OK? OK, there's also the term where E is equal to F, which of course is just the expectation. So let's just say I take that out before I apply anything. But now what is this? This is just the expectation squared, basically. I mean, the diagonal's a little off, but it doesn't hurt to add more on the diagonal. OK. So what have I shown is that the second moment is, is only a tiny bit bigger than the first moment. This means I have concentration, right? So the variance of x, just by math, is n to the minus c times this thing squared. Now use Chebyshev. Exactly as we did in lecture 1 or whatever. Or I didn't do in lecture 1. OK, so this automatically gives us concentration. OK. I have my wallet in my pocket, which is maybe a bad thing. So much chalk on me, my God. Thank you. OK. OK, so now what I'm going to do is show that we can control the maximum degree of the open graph. OK? So lem, so actually, let me just make life a little bit simpler. I'll just focus on a single vertex. And then we can just union bound over this. So let x be some vertex. Then, and of course, assume that this AI holds of the graph that you gave me. OK. And now I'm interested in the maximum degree of this guy. So pi plus 1, So the open degree, the size of the open neighborhood, after I've sprinkled in the next step, is at most, OK, some error term here, which we're not too fussed about, times what it should be, theta I. I'll just write this, si plus 1 times theta I. And this is at least 1 minus some number big enough here that I can union bound over all vertices. I mean, I even could get something almost exponential here, as you'll see in a second. OK. OK, so let's prove this. Sometimes I look at my phone, and it doesn't really go into my brain what's happening. OK. OK, so what's going on here? Let's draw a picture. I have my vertex x, and it has a bunch of open neighbors. This is now at step I. OK. Oh, my shoe came tight. Any shoe tying questions? Front row? OK. This is my open neighborhood. And now what I want to say is when I sprinkle in the rest of the world and in here, a bunch of these edges are going to get closed. And what I want to say is that enough of these edges get closed. OK. So what I'd like to do here is the following. So it's going to be a little bit messy. So I'm just going to rename things to make it cleaner. So this is actually the mean here. So this is we know what the maximum degree of the original thing was. It was theta I plus 1, basically. Oh, I forgot an n, sorry. The maximum degree originally was this. So what's the expected degree of this vertex? Well, I just multiply by the probability each edge survives. So the mean here is exactly this business here. So theta I times n. Okay, and now what I want to do is the following. So it's kind of like a moment argument, but this argument is just going to work for this one-sided inequality. In fact, it's sort of important for us that it's one-sided here. So here comes the trick, okay? What I'm going to do, and of course the hint is I want to use that lemma somehow. The trick is this. I want to consider, so I'm going to fix some number t, actually. T is going to be like some big polylog or whatever, something like this, or even a small polynomial is fine, okay? Okay, and I'm going to count the number of k1t's that look like this. So the center is this, and I have t vertices down here. And I want to count the number of them that survive into the next round. Okay, that's kind of like a moment argument. So let z, sorry, I said put t is some big polylog. That was supposed to be a big C. This guy, this be the number of kt1s centered at x that survive into OI plus 1. So the whole thing survives open into the next round. Okay. And now I'm just going to estimate this probability in two different ways. Or sorry, estimate the expected value, rather, in two different ways. So on one hand, this expectation is always at least the probability that we care about times something. OK, I'll just write it in this thing. So this is always at least mu, thank you. OK, so what happens on this event, when it's much bigger, I expect many more k1t's to contribute to this count. How many? Well, if it's that size, it's 1 plus epsilon mu guys survive, and I can choose any t of them. OK, just sort of. OK. But I can also, using this thing, actually estimate very precisely how many k1t's survive. So this expectation is equal to the sum over all possible k1t's. So this is, how do I even write this? With center x and leaves in the neighborhood at stage I of the vertex. So this is the sum over all such k1t's. Okay. And again, I actually have very good control over this. So it's simple. So this was at step I. Just select any t guys here, and now ask the probability that they survive, bound the probability to survive using this. So this is at most neighborhood of I circle, choose t times the probability to survive. Well, I know exactly how many edges there are. So this is si plus 1 t, OK, times some error term, which is small enough that I'm not going to care about it. So I fixed x here. Yeah, sorry. So to finish the proof of the max, you have to union bound over this. Yeah, thank you. Good. And now I have these two inequalities, right? So this guy is at most this thing. So now I can bound the probability here as the ratio of these two things, and I'm done. So actually, maybe that's all I'll say there. It's really just the one line of rearranging. But let me point out one facet of the line that I'll skip. Notice here, this is the number of open neighbors at step I. So here I'm crucially feeding into it the information that my AI holds. So it's this nice thing when the degree congestion is exactly bootstrapping itself. So the fact it holds at step I implies it holds at I plus 1, and so on. Which is good. Wow, no time. OK. OK, and this is basically, OK, so there's a couple more conditions to check, right? Degrees and co-degrees. You can prove both of these things with the same idea here. For these cross degrees, the ones that are in GI and the ones in open intersection OI, you need a little extension of this lemma that takes into account both sets. But I left that as both graphs. So I left that as an exercise to prove. OK, so in the remaining 10 minutes or so, OK, so this really shows that the process runs for long enough. In the remaining 10 minutes, I'd just like to show how to do this independent set calculation. Okay. And by the way, actually, you can get all this to run to the very end. So the true density of the triangle-free process is actually no harder than this, where we're going to use this result that we only run to this delta proportion of the total time comes really in the independent set calculation here. If you want to do the proper independent set calculation, you do have to fight more. But we don't have to do that here. OK. So how to bound. Is there any questions at this point, actually? So we can run it to time t with high probability. We've sketched the proof of this. How do we bound this business here? I feel like there's a question emerging somewhere. No? OK. False alarm. OK, so that's the probability that we want. We're also always allowed to assume that, say, all these events hold if we like. OK, because we know that they hold with high probability. Now I'd like to deal with this event. OK, unsurprisingly, I want to use a union bound over all independent sets. So let's just do that right away. Sorry? Thank you, yes. I mean, okay. So, right, and I should probably remind you what k is. K is going to be like a large constant, which will actually depend on delta. I might as well put delta in there, why not? Times root n log n. So large constant times root n log n. And this is really our objective. OK, so I'm going to union bound over all possible sets of that size. And I'm going to multiply by the probability that I is independent. And now here, I really mean g at most t and not g primed anywhere. OK, so this will require an extra trick. We've already seen one way of dealing with this by removing these triangle factors. That's not what I'm going to do, but I might not even get to it anyway. So that's not what will be in the notes. OK, so I need to understand this probability. I'd like to just sketch for 1 second about how we do that. So here's fix an independent set I. And if it's really independent in the whole graph, we had to have the following thing. OK, forget about the fact I'm deleting edges. I'm passing this maximal subgraph. Let's put that aside for a second. OK, because there's another problem here. OK. I want to think about this probability. OK, so I'm running this process. I'm throwing edges down in this independent set. And of course, in every step, I need to basically miss this independent set I. So at the ith step, I'm, like in any independent set calculation, I'm going to get a 1 minus pi, actually do I plus 1, to the power of what? So now it's not going to be k choose 2, right? Because I'm closing edges in here as time goes on. Lots of edges will be forbidden in here as time goes along. But what I could hope is that I have not k choose 2 edges here, but k choose 2 times theta I edges here. Because that's the density of this graph. We expect it to be somewhat random-like. And so we expect this many edges in here. Okay? And so now, what is this probability? And let's even give me here I don't care about determining the constants. You can even give me a constant here, and I feel happy. So what's this? This is at most the sum of this pi plus 1 theta I, k choose 2. OK, pi plus 1 theta I, we know what that is. It's a particular fixed value, so that's gamma over root n. And I know how big the sum is. I really know I go up to take t steps. So what is t? T is 1 over gamma times root log n. OK, so the gammas will cancel. Minus, thank you. Ooh. And now I claim that this thing will compete with this. OK, so let's put this over here. So this is at most n over k. Let's pull out a factor of k from both terms. OK, so that's the logs cancel. Oh, I forgot a delta too, sorry. Delta root log n divided by root n times k. There's a k here. And now I reminded you what k is. So that was c over delta times n log n. OK, so these root n's cancel. These log n cancels combine to form log. The deltas cancel. And I have constant times log, which is exactly competing with a polynomial. OK, so it's exactly the kind of behavior that we expect. OK. OK, so we're at 3 o'clock. But let me say one more minute. OK. So that's the story. And in this case, the story is really close to the truth. And I just want to describe how we guarantee something like this. OK? So I need to show that for every possible independent set in my graph, the number of closed edges, like the number of edges inside of that independent set doesn't get too closed up. And here's a very simple idea. So here's my independent set. OK. And now let's line up all the vertices outside. And in one round of the process, a vertex here is going to send some edges over here. In fact, we expect it to send at most like log edges over here. Now, there might be a few edges, so a few vertices rather, that send lots of edges, say more than n to the delta. Let's pull those aside, and we have to deal with them in a different way that I don't have time for now. But imagine everything here has at most n to the delta neighbors over here. Now what we can do is use a concentration result. So what does concentration say? My random variable, which will be my number of open edges in here, is concentrated about its mean unless there's any big jump in the way that I close edges here. Right? This is like Chernoff inequality. McDermott inequality will work here. Pretty much anything of this form. And why are the jumps bounded? Because if a vertex sends at most n to the delta edges over here, it can close at most n to the 2 delta edges inside of here. And this is enough to get Chernoff to work. I'm not going to do the calculation. But that's how you prove this. So you guarantee that you have this so that you can make this calculation run and get the bound on the independence number. OK, I'll stop there. Thank you very much.